Alright, so I'm making this video because for the people that did sign up for the tutoring session, for some reason the video or the tutoring session video conference option did not work, so obviously I couldn't do a tutoring session, so I'm just going to make a video answering every single question on the study guide to detail and how I would when I was tutoring it. And I'll just go ahead and post that. So I have the study guide here printed out. And now his study guide that he posted is different. All teachers, they change it up every single semester. I don't know why. Even if it is the same exact questions, they like to change it and put it in different orders and say to confuse people. Just I don't know. But most of them are the same exact questions. Some of the questions I just combined it into a few more, and I'll go over them. And for some reason, I forgot to talk about the 3 energy systems, and I'll go over that also. And I'll also go over some questions that people are having about the study guide versus my study guide versus his notes. Because again, I don't know why they decide to teach it different every single semester. It's pointless. You can't teach a concept and keep teaching different every single semester. But, so I guess we'll just start with question 1. Now, exercise physiology is all about, like, if you just understand the basics of exercise physiology, what the point of it, what the whole purpose of the subject is, it all makes much better sense and makes much more enjoyable time to understand it. All it is the study of how the body adapts to exercise. And the body's highly adaptable, as you know, and the muscles are highly adaptable, so they always adapt positively to exercise, to stress, to resistance training, to anything. And they just adapt. So really, this whole subject is about how the body gets stronger with exercise, with resistance training, with stress and everything. So that makes the subject much more enjoyable when you think about it that way, that the whole subject is just of how the body improves itself and how you get better. And any subject where you talk about how you get better when you exercise, it starts making sense more when you start exercising and when you start lifting weights and doing cardio and all that good stuff. You start realizing, you start thinking, oh, how is my body getting stronger? My body is doing this and this and this. Knowing the exact process isn't really interesting, but knowing exactly how your body is getting stronger, what it is exactly doing and adapting, makes it a lot more fun to understand. Instead of just memorizing stupid facts, memorizing numbers, and be like, oh, glycolysis, 38 ATP, everything. Just memorizing numbers is not the way to learn. Always, you want to know the concepts and how these things relate to real life. And when you actually understand all these things, all of it relates to everything. Because all of us, I'm sure in this major and at this point, all of us do some form of exercise. We either run, swim, work out, lift weights, I don't know, and now this all makes sense and you're seeing exactly how it affects your body. And I'll go into a lot of detail more. You see, I hate supplements. Well, I don't hate supplements, but I hate all the shit they sell on GNCs and everything. And this science disproves the majority of the things they sell. So it's pretty interesting knowing exactly how the body reacts to a lot of things like creatine, all the shit protein they sell for ridiculous amounts of money, all the fat burning stuff they sell. And then you actually understand the science and you realize it doesn't do anything. So it's pretty interesting. Okay, so now, after I just got off that we'll go to question 1. Question 1 is just asking, or my question, we'll go on my study guide, not his study guide. But my question 1 is just knowing the difference between aerobic and anaerobic metabolism. Okay, now the way he teaches it is with or without oxygen. Aerobic means with oxygen, anaerobic means without oxygen. That is right to an extent, but that's not the way. Like when you go on to when you take Dr. Panton in exercise testing, and then you ask her about this, the way she teaches the graduate exercise phys, and she does not teach that. The graduate books do not teach with and without oxygen. And it's just it's an outdated concept. I mean, it's true to a point, but exercise physiology is constantly changing as we figure out new things, so that is not true anymore. I mean, yeah, that will serve if that's what he taught, but that's not 100% true. What is a better definition is fast glycolysis and slow glycolysis. Those are better words to describe anaerobic and aerobic. So what they mean, though, they're referring to the systems of how the body metabolizes glucose, or a simple sugar molecule, and makes ATP. So just think of your body as a car and glucose as fuel, gasoline, unleaded gasoline. So you take this simple glucose, or the simple sugar or glucose, same thing, interchangeable, and now you break down this glucose, because it's a 6-carbon molecule, and as it is, it's not energy. It has a potential to give you energy, but you have to break down this 6-carbon glucose to get ATP through many steps. And ATP is the thing that actually fuels our muscles, causes muscle contraction, causes every single fucking reaction in our body. It's because of ATP. So ATP is pretty important. Carbohydrates are pretty important. So that's also, this will tell you that low carb diets and zero carb diets are retarded. You need carbohydrates to live. Okay, so there's two systems, aerobic and anaerobic. And glucose, regardless, always the very first section is it goes from glucose, one 6-carbon molecule of glucose, to 2 3-carbon molecules of pyruvate. So you're taking a bigger molecule of 6 carbons and you're splitting it to 2 3-carbon molecules. So it splits to 2 pyruvates. And this process is called glycolysis. And this always happens in the cell's cytosol. That will be a question. It's a question in every single class involving physiology, metabolism, exercise testing, graduate exercise test phys, everything, exercise phys. So you have to know that glycolysis happens in the cell's cytosol. You have all this sugar from your food that you eat, it's floating in your bloodstream, and now when you want to use it for energy, it has to go into your cell, into the cytosol of the cell, and that's where it's broken down to 2 pyruvates. So glycolysis happens in the cell cytosol. That will be a question. Now, once it gets into the cell cytosol and glycolysis, a 6-carbon molecule breaks down to pyruvate, that is called glycolysis. That's glycolysis. And this process does not involve oxygen. It happens regardless. And then once you have your 2 molecules of pyruvate, either pyruvate can form lactate or it can enter the mitochondria and form acetyl-coA and more ATP. Now, if it forms lactate, that is the point that's technically the point where it's referred to as anaerobic once it forms lactate. Because when it forms lactate, we'll go over why we form lactate. But once it forms lactate, it's coined anaerobic. Now, if pyruvate enters the cell's mitochondria to form acetyl-CoA, go to the TCA cycle, and form more ATP, then it is coined aerobic, or with oxygen, because it's with oxygen because the final receptor at the very end of the cycle is oxygen. That's the same oxygen that we breathe. So thus with oxygen, even though oxygen is not involved until the very last step. So as you see, so that's aerobic and anaerobic. Now, the reason it's called fast glycolysis and slow glycolysis is glycolysis happens extremely fast. It's just breaking your 6-carbon glucose to 2 pyruvates into the cell cytosol. That happens very fast. That only takes around a minute to 3 minutes to happen. That's why glycolysis is a predominant fuel for intense exercise, up to 3 minutes. So that's why it's referred to as fast glycolysis, because whenever we need energy extremely fast, you go out and sprint 800 meters, or you go out and do something really fast, we need energy fast, you're dependent on glycolysis or anaerobic respiration, so they call it fast glycolysis. Now, if you're out running 4 miles, or you're doing some cardiovascular, an endurance event, or you're cycling or you're swimming, and you don't need energy right away, then it's called slow glycolysis, because the glucose has time to go into the mitochondria and form more ATP ultimately. So slow glycolysis. So fast and slow glycolysis, or anaerobic and aerobic, whatever you want to refer to it as. Okay, so in question 2, what is ATP? ATP is the energy currency of the body. Without ATP, our bodies cannot function. Every single thing in our body takes ATP. Muscle contraction, the breakdown, the activation of every single cell, swallowing, peristalsis, everything. Everything involves ATP. Breathing involves ATP. So if you didn't have ATP, you cannot live. Your heart cannot beat without ATP. You can't really do anything without ATP. So it's the main energy currency of the body. Now, everything that we just went over with anaerobic and aerobic, or taking one glucose molecule and breaking it down to ATP, the whole point of forming this ATP is to form muscle contraction when we get to the end of the guide. So ATP fuels everything in the body. So it's like money. You can't buy anything without money. You can't do anything in the body without ATP. Same thing. Now, ATP, if he asks for the structure is adenosine triphosphate. It's an adenosine molecule attached to 3 phosphates. Now, to actually get energy, of how it functions is you get energy when you cleave off the last phosphate in the 3-phosphate ATP to ADP, or adenine diphosphate. And by cleaving this phosphate off, you get a massive amount of energy. And that's how you get energy. Just by, you have to cleave it. ATP by itself, it's great. It's just like your money by itself is good. Like you have a lot of money, good. You have a lot of ATP, good. But it's not useful. It's not put into action until you actually split the third phosphate. Just like money is useless by itself, it depends what you do with the money. Once you actually spend it, then it's useful. Just like ATP. ATP is good by itself, but you have to actually do something with it. Or you have to split the third phosphate. Okay. So question 3 is describe glycolysis. Know the net yield of ATP depending on what substrate you use, glycogen versus glucose, and all the other good stuff with NADH and FADH. Oh, we didn't talk about that right now. And lactate. Okay, glycolysis, as we went over pretty much, is the breakdown of glucose or simple sugar to get to pyruvates. Right now we're just talking about glycolysis. So you have your 6-carbon molecule glucose. A good metaphor to think about how you're breaking down glucose eventually to 2 3-carbon molecules and then you're forming your ATP is, think about going to a laundromat and you need quarters and you only have a $10 bill. Well, that's the same thing with this. You need ATP, but you have a 6-carbon molecule glucose. So you have to break down this 6-carbon molecule to 2 3-carbon molecules, and then those 3-carbon molecules break down even more. Just like breaking down a $10 bill to a $5 bill, into a $1 bill, and then to quarters. It's the same metaphor. So you have your 6-carbon molecule glucose, which is like a $10 bill. You have to break it down to 2 3-carbon molecules in order to start getting energy. By itself, it's not that useful. You have to break it down. So you eat your glucose and everything. You eat your carbohydrate. That's good and all. Now you have all the sugar flowing in your bloodstream. Now, all the machinery, like mitochondria, the electron transport chain, all the enzymes to actually break down this glucose are inside your cells. So that would tell you right away you need to get the glucose inside your cell. So thus the glucose has to enter the cell into the cell cytosol. So again, glycolysis does not start until the glucose is inside the cell. Now, I don't believe he went over how glucose gets into the cell or if you need to know that, but it's done via insulin. And you'll have to know that for the third test, I believe. But anyways, glucose is inside the cell now. Now, once glucose gets inside the cell, what is stopping glucose from leaving the cell? Glucose can just leave the cell as easily as it enters the cell. So to prevent it from leaving the cell, it has to be phosphorylated to glucose 6-phosphate. And this is why the very first step of glycolysis takes 1 ATP. So glucose acts with ATP, forms glucose 6-phosphate, and thus you lost an ATP. So you're probably thinking, wait, hold on, we're trying to make energy, we just lost energy, so what is the point? What is the deal? Well, the point of using that ATP was to keep glucose inside the cell. So that was a necessary step. So you had to take that first step to lose ATP. So far we have glucose 6-phosphate and we lost an ATP, so we're in debt. Well, now we just paid an ATP molecule. So the next step is it goes through something else, you don't have to know the steps, but then the next step after that is it takes another ATP. So form fructose 1,6 bisphosphate. Okay, so now you have your fructose 1,6 bisphosphate, it's still a 6-carbon molecule, and you lost 2 ATP. I don't know if numbers are important. I'm not going to say what is important because I'm not in the class. I don't know what's important, but in an exercise physiology sense, in a recurring subject, this is in every single class. You have to know when glucose takes energy. So to start glycolysis, you lose 2 ATP. And I'm not sure if it's important to know the steps of when that happens. But now we can start breaking it down and forming ATP. So now we break down our 6-carbon molecule to 2 3-carbon molecules to a glyceraldehyde 3-phosphate. We can skip all the steps. But you have 2 glyceraldehyde 3-phosphates, and both of them are 3-carbon molecules. So now, when you actually look at the steps, and if you want to learn them, every single step after this is doubled. So there's 2 reactions of each. This is why we form 4 ATP from glycolysis. So if you want to look at the steps, since each reaction is happening twice, this is why we form 4 ATP. But you also have to remember that we lost 2 ATP at the beginning, so you take that 2 into account, so we only formed a net of 2 ATP. So glycolysis only forms 2 ATP. And that's going to be important to know. Can't say if it's important in this class. I can tell you it's important in exercise physiology. Everyone asks that question. Glycolysis only forms 2 ATP. And it also formed 2 NADH. So if you keep a running count of what we have right now, we have 2 ATP, 2 NADH, and also 2 pyruvates. And pyruvates are the 3 carbon molecules. Okay, so now you have 2 pyruvates in the cell cytosol with 2 ATP and 2 NADH. Now, what lactate is and why we form lactate. Now, the 2 pyruvates can, if you need energy really fast, you form lactate. The reason for this is, okay, now if you look at the steps, in order to get to pyruvate, an NAD is used, and NAD is reduced to, is that right? No, NAD is oxidized to NADH. So, thus that means it takes NAD in order to form pyruvate. Again, you won't have to know that probably. You just have to just know you take an NAD to form pyruvate by looking at the steps because you form NADH. So that means to keep glycolysis running, you need NAD to keep it running. Now the cell only has a set amount of NAD. That's what actually NAD is niacin. So you could eat more niacin up to an extent to get NAD, but NAD will eventually run out and not be able to keep up with the amount of glucose because you have a lot of glucose in your blood, but you only have so much NAD. So eventually you run out of NAD and you can't form pyruvate anymore, so energy production stops. So in order to get more NAD, and since the production of pyruvate took NAD, you can reduce NADH to NAD by turning pyruvate to lactate via lactate dehydrogenase, an enzyme. So that's why you form lactate. He's going to ask specifically, why do you form lactate? I don't know if it's on this test or if it's on another test, but you have to know specifically why you form lactate. And I can tell you right now, the answer of because you need energy fast is not good enough. You don't have to know why you form lactate in order to keep glycolysis running by regenerating NAD from NADH. So that's why you form lactate. So by itself, lactate production isn't bad because you have to form lactate in order to keep the cycle running. But the bad part about lactate is it's extremely acidic, so eventually it builds up the acidity, and that can stop muscle contraction and mess up a lot of things in the body. But again, you don't have to, that would be on another question. But that's why we form lactate, to keep the cycle running. Now the next thing I went over is glycogen. Now you won't have to know this. This will be a concept you have to know. Now, if you use blood glucose, glucose is in the blood, you have to bring it into the cell and phosphorylate it so it doesn't leave the cell. This takes an ATP, and thus you're 1 ATP in the whole. Now, if you use glycogen, if you get glucose from glycogen, glycogen is a storage form of glucose that's already in the cell. It's reserved. It's just like stashing something away, putting money in a jar or something, not touching it. That's the same thing as glycogen, just putting stuff in storage to keep it when you need it, an emergency fund of glucose kind of. So since glycogen is already in the cell, if you get glucose from glycogen, you can just easily cleave off the glucose from the glycogen. And since it's already in the cell, it doesn't have to go through, you don't have to worry about it leaving the cell. It doesn't have to be phosphorylated to glucose 6-phosphate. So thus, if you get glucose from glycogen, you don't have that first step where you lose an ATP. So ultimately, if you use glycogen to glucose, you're going to have one more ATP in the very last step. Whereas if you use blood glucose, you're going to have one less ATP. So blood glycogen is more favorable. Glycogen is more favorable to use because it ultimately yields more ATP. But you run out of glycogen very fast. But he's going to ask what's the difference between using glycogen versus blood glucose? The reason being, glycogen yields more ATP ultimately because you don't have that first step where you lose 1 ATP to phosphorylate it. Okay, so now he asks, what is the potential of glucose metabolism to form ATP? Directly, glucose metabolism does not form ATP. It forms NADH and FADH, which we'll go over in the citric acid cycle. And these are very high electron yielding molecules, so they have the potential to form a lot of ATP from electrons. So we'll go over the exact numbers later, but those are the potentials in NAD and FAD. Those are what forms the ATP in the electron transport chain. Again, we only form lactate if exercise is extremely intense. We need energy very fast. And again, the formation of lactate is really to regenerate that NAD so we can keep the cycle going. blah. Okay, so in the question 4 is describe the Krebs cycle. Talk about the Krebs cycle, what happens to pyruvate before it enters the Krebs cycle, and all the high energy molecules. Okay, so now glucose entered the cell. It went to glucose 6-phosphate in the cell cytosol, broke down to 2 pyruvates. Now what happens at this point? If you need energy extremely fast, pyruvate can be reduced back to lactate in order to get another NAD, and that would be considered fast glycolysis or anaerobic. That's if you need energy very fast. Now, if you don't need energy fast, the pyruvates can enter the cell's mitochondria, the energy powerhouse of the cell, and once it enters the mitochondria, it's considered aerobic. There's no turning back. Pyruvate can't leave the mitochondria. Okay, so now let's follow 2 pyruvates. They enter the cell's mitochondria. What happens next? Now, in the mitochondria, pyruvate has to be metabolized to another molecule called acetyl-coA. So this 3-carbon molecule pyruvate loses a carbon to turn to a 2-carbon molecule acetyl-coA. And in the process, it forms an NADH, and of course you lose a carbon, and this is the same carbon that we exhale. This is where all the carbon dioxide comes from, is through the citric acid cycle. Okay, so what happened? We turned a 3-carbon pyruvate to a 2-carbon acetyl-CoA, lost a carbon, that's not important, but we gained an NADH, that's important. So now we have acetyl-CoA. Now what does acetyl-CoA do? Acetyl-CoA is a 2-carbon molecule. I suggest you looking at a picture of the citric acid cycle if you want to actually understand it, but the 2-carbon molecule combines with a 4-carbon molecule oxyl acetate to form another 6-carbon molecule. The reason for this is once we go through the cycle, the whole point of going through the cycle is to get NADH and FADH. And in order to do that, we have to have carbons. The electrons come from carbons. A 2-carbon molecule doesn't really have a lot of potential to form a lot of NADH and FADH as compared to a 6-carbon molecule. So that's why we form this 6-carbon molecule called citrate, or citric acid. They're the same thing. Now it goes through a bunch of more steps I don't think you need to know, but citrate forms isocitrate, forms alpha-ketoglutarate, blah, 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 forms a bunch of steps. The important part is through all these steps, you form 3 NADH, 1 FADH, and 1 GTP. I don't know if you have to know the steps that form these things, so I just skipped them. I didn't explain them. But if you need to know them, just tell me. We're looking at a picture. Doesn't matter. But the whole cycle, so one pyruvate turns to 1 acetyl-CoA, and that 1 acetyl-CoA forms 3 NADH, 1 FADH, and 1 GTP in the cycle. But you also have to account for going from pyruvate to acetyl-CoA also formed 1 NADH. So really one cycle from pyruvate forms 4 NADH, 1 FADH, 1 GTP. But you have to remember that there's 2 pyruvates. So this happens twice, so just double everything. So altogether, from 2 pyruvates, you form 8 NADH, 2 FADH, and 2 GTP. Again, this is a final tally of numbers. He can, depending on what he asks us from starting from, these numbers can be different, so don't take my word for it for memorizing the final numbers. If he says starting from acetyl-CoA, 1 cycle of the TCA cycle, then yes, it's 3 NADH, 1 FADH, 1 GTP. If he says starting from pyruvate, 1 cycle, it's 4 NADH, because from pyruvate to acetyl-CoA. So it can all depend on what your starting point is. But that's the whole point of the cycle, just to form these high energy molecules. And that 6-carbon molecule is breaking down as it forms these NADHs back to oxyl acetate. That oxyl acetate attaches back to that second pyruvate and it continues the cycle. So, cycle. Okay, so now question 5 is describe the electron transport chain. Why did we form NADH and FADH and the difference in energies? Know the general mechanism. Okay, so the electron transport chain is on the anomitochondrial membrane. If you're looking at mitochondria, it has 2 membranes. The TCA cycle happens in the matrix or the outer membrane. The electron transport chain is on the second membrane on the membrane. I don't think you know where it is, but it's on the anomitochondrial membrane if he asks. Now the electron transport chain is really a series of 4 complexes, and the point of these is to take the electrons from these high electron molecules, NADH and FADH. It takes these electrons and it can turn these electrons, it can use them to fuel the, so what's the word I'm trying to think of? I want to say fusion, but it uses to fuel the combination of ADP and phosphate at the very end of the cycle, the very last complex, and these turn to an ATP, and thus you get your energy. So that can tell you the more electrons you have, the more ATP you can form. So the metaphor I used is, think of it as a tower. You have 4 complexes: complex 1, complex 2, complex 3, complex 4. Complex 4 is the one that takes all the electrons, forms your ATP, and you have your ATP. Now NADH enters on the very top complex. Now every single complex takes electrons and pumps them out into the membrane. So it goes to the first complex, it gets electrons pumped out. It goes to the second complex, gets more electrons pumped out. Third complex, more electrons pumped out. Fourth complex, all those electrons come back in and form ATP, or fuel the formation of ADP and phosphate to form ATP. So NADH enters the top complex. So ultimately, by numbers, it forms 3. It has the potential to form 3 ATP. It has enough energy to do that. Now FADH enters in the second complex. So first complex, second complex, FADH enters right here. So since it enters in the second complex, it only pumps out electrons there, there, there. So ultimately, it pumps out less electrons than NADH. That is why NADH only yields 2 ATP compared to, that's why FADH only yields 2 ATP compared to NADH, which yields 3 ATP. Now, you might have read in the books, I don't know, but they're constantly changing how much energy it yields. In later books, they say NADH only yields 2.5 ATP and FADH yields 1.5 ATP. Go with whatever number he says. Again, it's not really known how much it yields, because theoretically it doesn't yield any energy, it yields electrons. But numbers that, the set numbers are 3 and 2 or 2.5 and 1.5. I don't know what he said, but if he said 3 and 2, go with 3 and 2. If he said 1.5, 2.5, go with that. And GTP is equivalent to an ATP. It doesn't do anything fancy. It goes through one reaction and forms ATP. Okay, so now here's the fun part. We can do all the math. Okay, so this is, like, he doesn't really teachers aren't really they're not really concerned about all these individual steps. All they care about is the end point. What is the point of forming all these things? Now let's add up all these steps and see how much ATP we formed. Okay, so now we'll just do some simple math. So now, okay, so from 1 pyruvate enters the TCA cycle, whole 1 cycle, that is equivalent to 4 NADH. Remember, pyruvate to acetyl-CoA, you get 1 NADH. Cycle, 3 NADH. So that's 4 NADH, 1 FADH, 1 GTP. That's 1 pyruvate. There's 2 pyruvates, so double everything, 8 NADH, 2 FADH, 2 GTP. Do some math. Each NADH is equivalent to 3 ATP, so 8 times 3 is 24 ATP. Each FADH is equivalent to 2 NADH, 2 ATP. Do some more math. It's 28 ATP. GTP is equivalent to 1 ATP. It's a 1-on-1 reaction, so that's 30 ATP. So are we done? Is that how much ATP one molecule of glucose gives? 30 ATP? I mean, no, because you also have to factor in, remember from glycolysis you form 2 NADH. Those are still worth 3 ATP, so you factor those in, that's 6 more ATP, that's 36 ATP. But you also have to factor in that glycolysis yielded a net of 2 ATP, so that's 38 ATP. So if he asks us what is the complete breakdown of one glucose molecule going through aerobic respiration or aerobic oxidation or oxidative phosphorylation, all those words mean the same thing, they're just fancy words for the same thing. I try to confuse you by changing the words. That is 38 ATP because again you do all the math. Now if he says how much ATP do you yield from glycogen instead of blood glucose? Blood glucose is 38 ATP. If he says glycogen, it's 39 ATP. Because remember, glycogen, you don't have to go through that first step, so you don't lose that first ATP, so ultimately you yield 1 more ATP, 39. So 38 ATP is from blood glucose. Glycogen is 39 ATP. Now I saw some students set a number of 36 ATP. 36, the number 36 comes from those 2 NADH that were from glycolysis. Those are in the cell cytosol, if you remember. NADH cannot cross into the mitochondria, so there's two shuttle systems. There's the maltate aspartate shuttle system and the glycerol 3-phosphate shuttle system. In my class, he never went over shuttle systems. He never mentioned shuttle systems. But just realize that those two NADHs do have to get into the mitochondria somehow. So that's the two shuttle systems. Depending on what shuttle system you use, like if you use the maltate aspartate shuttle system, the NADH is shuttled into the mitochondria. That's 38 ATP. If you use the glyceraldehyde 3-phosphate shuttle system, the NADHs enter the mitochondria as FADH. So two NADHs turn to two FADHs. You get ultimately two less ATP. Don't know if you went over that, but if you did, here it is, I went over it. Question 6 that I have, following my study guide, not his, is give a general description of beta oxidation. I saw in his study guide he did not even talk about beta oxidation, but I'm going to since it was in my class. Just a general description. You don't need to know all math and everything. You might have to if he asks it, I don't know. But general description is going through all before with glycolysis, the citric acid cycle, the electron transport chain, all that was using glucose for energy. Your body has 3 macronutrients: carbohydrates, or the same thing as glucose, fats, and proteins. Your body is extremely adaptable. It's not going to just depend on. It's not just going to use glucose to make ATP. Because say you listen to a stupid fad and cut out carbs from your diet completely. Well, you can still get ATP from fats and from proteins because the body is not going. The body's always going to have backup systems. It prefers to use glucose; it's more effective. But if it has to, it'll use fat and protein. If it really has to, it'll use protein. It prefers not to use protein because you can think proteins are used to build muscle, so you don't want to use protein for energy. But if you have to, you will use fats. Fats can ultimately yield a lot more ATP than glucose. The total breakdown of glucose, blood glucose, only yields 38 ATP, but it does it pretty fast. Now, the total breakdown of a fatty acid can yield hundreds and hundreds of ATP, but it takes an extremely long time to use. So it's much more effective in the sense that it gives more ATP, but it's very, very time consuming. And mostly the body needs energy fast, so that's why it depends on glucose. But if you're going out there running 5 miles or running a marathon or doing something, then you don't need energy right away. I mean, you'll still break down glucose. You always break down glucose. But you break down more fat because you have time to break down all that fat. So you can use fat to break down ATP. It takes a much longer process than using glucose. It's much more efficient. I mean, glucose is much more efficient because it's faster. And when you find out it takes less oxygen to break down the same amount of glucose, so that's why our body prefers to use glucose. But fats yield much more ATP. So that's why we have an abundance of fat in the body, because that's why we live on fat if we ever starve ourselves. Okay, so when I say fats circulate the body as triglycerides, you might use triacylglycerides. It's the same exact thing. Now say we need to use a fatty acid for energy. First, that fatty acid has to enter the mitochondria. In order to enter the mitochondria, it has to be activated, attached to carnitine, blah, 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 cross the mitochondria barrier into the mitochondria. Now, I was taught in this class, and also taught in later classes, that it takes 2 ATP to activate that fatty acid. I've had a few students say it only takes 1 ATP that he said in his notes. If his notes only said 1 ATP, go by his notes. I never want to tell you the wrong thing and you get a question wrong because I told you the wrong thing. So always go by what his notes say compared to what I say. But it's true, it does take 1 ATP, but remember, ATP, the reason it gives energy is because it splits to adenine diphosphate, and that gives the energy. In order to transfer a fatty acid into the cell's mitochondria, it actually splits twice into AMP, adenine monophosphate. That is why it is equivalent to 2 ATPs, ultimately with energy yield. But again, whatever his notes said, go with. So now you have your fatty acid in the cell's mitochondria. What happens? A fatty acid is a repeating chain of carbons and hydrogens. So it's carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. That's what fatty acid is. Now, if you remember from glycolysis or from the TCA cycle, what enters the TCA cycle? A 2-carbon molecule. So we don't want a 16-carbon molecule, which is the most common fatty acid in the body, is kind of useless because it can't enter the TCA cycle. You need a 2-carbon molecule. So what do? You break down this fatty acid 2 carbons at a time so you can get your 2-carbon molecule. Now every time you cleave a fatty acid to a 2-carbon molecule, just cleaving it yields 1 NADH and 1 FADH. So 1 NADH, 1 FADH. If you remember, an NADH is 3 ATP and FADH is 2 ATP, so every cleave gives you 5 ATP. So now you have a 2-carbon molecule plus 5 ATP. What is a 2-carbon molecule? A 2-carbon molecule is acetyl-CoA, so it does the same thing. It enters the TCA cycle, gives you your good old 3 NADH, 1 FADH, and 1 GTP. Same exact process. NADH is 3, FADH is 2, GTP is 1. Do the math. It's 12 ATP because plus that 1 NADH and 1 FADH just from cleaving it, so it's 17 ATP. So each cleave ultimately gives you 17 ATP. So you can now, you have to draw out a fatty acid to understand this, but say you have a 16-chain fatty acid. You can only cleave a 16-chain fatty acid 7 times, not 8 times, just by dividing by 2. Because if you draw it out, you cleave, 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 cleave. In the very last cleave, you do get a 2-carbon molecule, but you only cleave 7 times. So you do 7, you can just do the math. 7 times 5, because each cleave is 5 ATP, that's 35 ATP. But you formed 8 acetyl-CoAs, so that last cleave gave you 2 acetyl-CoAs. And you have to draw all out to see this. So you do 8 times 12, give you, I can't do that math in my head right now for some reason, but it gives you that number. And you just add it up, and there you go. But you also have to subtract the activation, which I say is 2, he says 1, go with what he says, and you get your final yield, which is 16-chain fatty acid yields 129 ATP if you subtract 2. That might be a question, I don't know. But that's what happens. So as you can see, the breakdown of a fatty acid yields much more ATP than the breakdown of a glucose molecule. But as you can probably figure out, breaking down a 16-chain fatty acid takes a long-ass time. So it takes a much longer time to yield a lot more energy as compared to glucose, which happens relatively fast, but yields less ATP. So if you have the time, fats are good. If you don't, glucose is good. Now question 7 is, which I see he didn't go over in the guide at all. Maybe he did, I don't know. But my question 7 is, what is a respiratory quotient, or RQ, and how is it determined? What does it mean? Respiratory quotient is a number. It's a rough estimate of what fuel source. It's a rough estimate of what kind of fuel source your body is using. Now, if your body, the formula for a respiratory quotient is VCO2 divided by VO2, or how much carbohydrate you're exhaling divided by how much oxygen you're inhaling. So VCO2 divided by VO2. That was a question for my class. Now, if this number is around 0.7, 0.7.5, that means your body is burning mostly fats, or it's using fat mostly for energy. If this number is higher, closer to like 0.9, 1, you can get higher than 1. But if it's around those numbers, if it's close to 1, you're burning mostly carbohydrates or glucose for energy. If it's around 8.5 or 0.85, you're burning a mixture of carbohydrates and glucose. Now you can get higher to like 1.2, 1.4, but that's usually an all-out exertion and a VO2 test. That's the only time you ever reach 1.4, because you're about to pass out. Your body's using much more oxygen than it has. You're about to pass out. You're about to run out of energy. Now, what these numbers mean is I think that's the next question. Yeah, that's the next question. Now, what these numbers mean is, next question is, what is the primary fuel for rest, light to moderate exercise, and heavy exercise? Now, when you're resting, you don't need energy right away. You have, like right now, I'm not in a need for energy, so my body is burning mostly fats. Now, when I say mostly fats, that doesn't mean 100% fat. You're never burning 100% fat. If you were burning 100% fat, every single person on this planet would be jacked. Every single person would have an 8-pack. They'll be ripped. They'll have 2% body fat. So you never burn 100% fat, even 80% fat. When I say mostly fats, you're burning 50% fat, 50% carbohydrates. So right now I'm burning 50% fats, 50% carbohydrates because I don't need energy right away. So the fatty acids have the time to be broken down to form ATP. So thus at rest, you're using mostly fats, 50-50. Now, in light and moderate exercise, it's the same thing. If you just go out and jog like 10-minute pace or something, you don't need energy right away, obviously. Or you might, depending on what shape you're in, but you won't need energy right away, so again, you'll be burning mostly fats, 50-50. Again, he might use numbers, I don't know. Numbers he used, he said 55% VO2. That's considered light to moderate. That's not considered too intense. You still use mostly fat for energy. Now above, see if I gave a cutoff. I did not give a cutoff, but usually the cutoff is 75% VO2. Above 75% VO2, or once you start breathing hard, then you enter the realm of heavy to intense exercise. Once you're in this realm, you're burning mostly glucose. Why? Because if glucose gives you energy extremely fast. If you're exercising extremely intense, if you're sprinting, if you're running hard, running a 5K, you're doing a race, you need energy relatively fast, so you're not going to depend on fat for energy when you need energy fast. So you're going to break down glucose, and your body's going to be depending on mostly carbohydrates for energy. This is another reason why low-carb diets are stupid. That's good, yeah, but if you're exercising, doing anything productive, and you need energy, you don't have that carbohydrates to form that energy, so you'll be pretty bad at sports. You wouldn't have that glucose to break down. So to answer this question in a basic sense, primary fuel for rest, fats, it's 50-50. Primary fuel for light and moderate exercise, fats, 50-50. Primary fuel for heavy and intense exercise is carbohydrates. Now, how this relates to the EQ, or the respiratory quotient, if it's 0.7, that means you're burning mostly fats. So what are you probably doing if you're burning mostly fats? You're probably resting, or you're probably walking or doing some really light exercise. So if your RQ or REQ, they're the same thing, depending on what he says or what's on the test, don't be confused. If it's low, like 0.7, you're probably doing light exercise. If it's high, that means you're burning mostly glucose, you're doing probably heavy exercise. And at the very end of that question, I explained why our body prefers to use carbohydrates for energy, because our body only takes 6 moles of oxygen to make 30 ATP, yet it takes 26 moles of oxygen to break down the same formation of fat. So that's why our body depends on ATP. Again, you don't need to know these numbers, but these numbers are showing you why our body depends on glucose. Why our body has adapted, they evolved to use glucose for energy. Our cells don't predominantly use fats, they use glucose for energy. Question 9 is define active and passive recovery and what effect do they have on lactate removal. Active and passive recovery just refer to what you do after you work out. Say you do a track workout, or say for people who do cross country and track, say you go run a mile, or you do a race, or you just did a hard workout on track. Now, after you just worked out for really vigorously, would you just stand still? Now, if you just stand still, that's considered passive recovery. You're not doing anything active. You're just passively sitting there. You're just chilling there like this. So say I just go up there, run a mile, come back down, sit on the couch like this. This will be considered passive recovery. This is not good. Because the reason this isn't good is because most likely you form lactate from exercise. You always form lactate. So I probably shouldn't say that. I would probably confuse. But lactate is normally considered for aerobic and anaerobic exercise. But say I just did anaerobic exercise and I formed a bunch of lactate and now I sit. So now I have all this lactate just chilling out in my blood. Now we'll go over another question, what happens to that lactate? Lactate has to be oxidized, it has to go to the liver. There's been some discussion about what happens to lactate, the fate of lactate, but most of it does go to the liver. Again, go with what he says, but you learn most of it does go to the liver, and it's recycled in gluconeogenesis and forms pyruvate, and thus pyruvate forms glucose. Whole cycle called the CoA cycle. So most of the lactate goes to the liver. Again, go with what he said. I'm saying most goes to the liver, go with what he said. But in order for lactate to get to the liver, you need, what does lactate travel, and what travels to get to the liver? How does stuff travel in the body? Through blood. So that makes sense that you have to increase your blood supply, your blood flow, to get lactate to the liver. In order to increase your blood flow, what do? You move. When you move, your body, your muscles just naturally contract, and this facilitates blood flow to the liver. So that's why they say always move after exercise, cool down after you work out, to facilitate your blood flow, to keep your blood from moving and keep it from pooling in your muscle, in a body part. So if you increase your blood flow to the liver, this ultimately is going to carry more lactate, more waste, more carbon dioxide, more nitric oxide, all the waste stuff you form from exercise. It's going to carry that stuff to the liver to be oxidized. So this is why active recovery is better for lactate removal, because it carries all the stuff to the liver. So it increases blood flow ultimately. What is a fatal lactate acid? Some discussion, many people, there's many different, really, the true question is lactate can do many things. There's really no one true question, and it's not even 100% proven what lactate does. It's an ongoing, it's a theory of what lactate does. You pick up a graduate exercise phys book or just Google, go to PubMed, say lactate removal, what happens to lactate? It's not 100% proven. A lot of things in the body are not 100% proven what happens, but we do know a majority of lactate does indeed go to the liver, goes through gluconeogenesis, forms pyruvate, is cycled back, pyruvate goes through gluconeogenesis, again, forms glucose, and thus you form glucose from lactate. This is called the CoA cycle. So we recycle a lot of lactate to form pyruvate to form glucose in the liver. It's called the CoA cycle. Some lactate is oxidized, and your body is just buffered out through a buffer system. But I'm saying the majority goes to the CoA cycle. I'm sticking with that. That's what happens to lactate. It's recycled to glucose. Now, question 11 is describe oxygen deficiency, oxygen debt, EPOC, all that good stuff. And this concept is interesting because it actually has real life experience. It's actually beneficial to know what exactly does, and you can actually play around with it. And this is how you get in shape, is through EPOC, and this is the easiest way to lose weight and get toned. Okay, so you have to see a graph to understand oxygen deficiency and oxygen debt. I can't draw a graph right now, but let's see. I can draw a graph. I'm not going to. But I don't have a pen. But the graph is essentially okay. I want to draw the graph. Okay. If you just look in the graph, it's much easier to understand oxygen debt and all that stuff. Okay. So this is the simple graph. That's not very helpful. Okay, well, anyways, the simple graph is this is you when you start exercising. So say you're starting exercising and you start at a number, just pick a number 0. This is how much oxygen your body is currently using. Your body is currently using a set amount of oxygen at rest. So right now I'm probably using a very low amount of oxygen to sustain my body and sustain my muscles and make them do whatever they're doing. Now, say this is how much oxygen you have when you start exercising. This is how much oxygen you need whenever you start exercising and you do the event. So say you go out there and you run a mile, or say you sprint a mile. It's the best thing. So say you go and you sprint a mile. So now, obviously, the oxygen that your body is using when you're resting is different than the oxygen that your body needs when you're sprinting. You can't sprint miles, so you're running a mile pretty hard. The oxygen amount is different. So this difference is called oxygen deficiency. It's the easiest name for it. Because you're deficient in the amount of oxygen you need from when you start exercise to what you actually need to sustain that exercise. Yeah, okay, don't need that anymore. So you have a deficiency. So this is what you actually need to sustain this exercise. This little line is what your body, the oxygen amount in your body is actually doing. Because obviously you can't jump from how much oxygen you have when you're resting to rates to how much you need when you start. You have to build up. You can't just jump. This is why when you start sprinting, you breathe it very hard. Your body isn't 100% ready. This is why when you're sprinting in a 100-meter race, like everyone doesn't start at max speed because you have to build up to it. So this is your body, and when this line is increasing, this is like you're physically exerting yourself, you're breathing faster, energy processes are happening in your body faster. I just realized something I did not go over, the 3 energy systems, but you're breaking down glucose, you're breaking down the phosphagen system, which I'll talk about, all that stuff, you're getting ATP. So this is what's actually happening. Now this line is considered steady state. Steady state is when steady state is easily reached. A way to explain it is, say you're in shape, you're a cross country runner, and you go out and run 5 miles. Well, eventually, well, not eventually, but you reach a point where you're running and you can easily sustain that pace. You're running 5 miles, you're not physically observing yourself, you're not dead after 2 miles, so you can easily sustain that pace. That's considered you're in steady state. You're exerting just enough energy that you need to keep that state. So you're steady state. You're going at a steady pace. So this is oxygen deficiency. Now, a metaphor that I use to explain it in easy terms is money. Say you start with $25, or you have $25 in your pocket. You want to buy something that's $100. So clearly there's a deficiency. You have to find some way to get that $75. So you borrow it. That's essentially what you're doing. This is a deficiency. You're building up that oxygen, or you're building up that money, or you're borrowing it. So you borrow that money and you get $100, and finally you reach steady state. Yay, you can go do whatever you want to do with that money. You have the oxygen, you can keep doing that exercise. So this is oxygen deficiency, this little thing right here. Now, with intense exercise, you never reach steady state. This is why, like if you go out and sprint 100 meters, you're going to be tired after you finish 100 meters. Or you go out and sprint a 400. That's an intense activity. Your body's relying on glycolysis. You're not relying on fats because you need energy extremely fast. You're never going to reach steady state, because if you reach steady state, then it wouldn't really be a sprint anymore. Now, this line signifies when you cease exercise. So say you started exercise, you built up your oxygen deficiency, and you reach this line. This line is when you stop exercising. So now you stop. Now, immediately when you cease exercising, your body does not immediately go back to what it was at its resting state. Your body doesn't, this is easily, in words this sounds confusing, but you can easily, everyone's been at this point, all relate to this. You go out, you sprint a mile, or you go run 10 miles or whatever. When you stop, most likely you're going to be tired. Most likely you're going to be gasping, or not, depending on what shape you're in, but you're going to be tired, you're going to be breathing hard, you're going to be exhausted and out of breath. So right when you stop exercising, you do not immediately go back to what you were before you started. So what they call it oxygen debt. So an easy way to explain it based on the metaphor is you had $25, you need $100, so you borrowed $75. It's kind of like the same thing with oxygen. You start resting with a certain amount of oxygen, you need another certain amount of oxygen to perform that exercise, so you borrow that oxygen. You literally don't borrow the oxygen, but for the metaphor, you're borrowing oxygen. And this is all, your heart rate's increasing, you're breathing harder, metabolic processes are happening in your body faster, but once you stop exercising, you immediately don't go back to zero. Just how you borrowed $75 to reach this $100, you're in debt, so you have to pay back that $75. So while you're paying back that $75, you're in debt. Thus the term oxygen debt. So that's why this line is like a slant, because you have to pay back that oxygen. And what is happening during this line is your metabolism is elevated, because when you start exercising, you rapidly increase your body temperature. So now during this debt, you slowly decrease your body temperature. You slowly build proteins, you build enzymes that you might have been using. You recycle lactate, you increase your blood flow, you replenish glycogen, you do all these things to fix your body from exercising. So your body is repairing itself, it's recovering from the exercise. And the whole time it's doing this, it's recovering, your metabolism is elevated. And this whole time your metabolism is elevated, and oxygen debt is called EPOC, excess post-oxygen consumption. So the personal training tip is you can use this mechanism to burn more fat, get a leaner body, get more in shape, and all that good stuff. This is why sprinting or high intensity interval training, I'm sure everyone's heard about it, HIIT training, high intensity interval training, it maximizes this EPOC theory by spiking up your heart rate, doing some high intensity training, spiking up your heart rate in like 2 minutes, and then you stop. And then while the exercise only took like 5 minutes, your metabolism is elevated like 2 or 3 hours after you stop exercising. This is why sprinting, most sprinters you see are ripped, they are jacked, they have six packs and everything, they have very low amount of body fat, they're very lean because of this. Because when you're sprinting, you're gaining an oxygen debt you're gaining a huge oxygen debt. You're taking advantage of this epoch. So your metabolism is extremely elevated after you stop exercising. Don't believe me, go out there, do sprinting exercises for like 2 weeks. You'll be surprised what happens to your body. You'll lose a lot of weight, you'll get very toned and everything. So that's a personal training tip. Now, the next question is, describe what happens during the alactic and lactic portions of oxygen debt. Now, going back to this little guy. Oxygen debt is the second thing. Alactic means without lactate, so you don't have lactate, you're not cycling lactate. Lactate means you have lactate, you're recycling lactate. Now, the words alactid and lactate, whatever hell you pronounce them, aren't really words, they're made up words. If you don't believe me, go Google them, go look in a medical journal, they're not words. They're just made up. But they're made up to give across a point of alactate is the portion of this whole recovery when you're not recycling lactate. So you're just replenishing glycogen, making enzymes, increasing your blood flow, lowering your heart rate, lowering your body temperature, all that stuff that doesn't involve recycling lactate. Lactate portion means you're recycling lactate, you're flushing all this lactate to the liver in the CoA cycle. Very confusing topic, but that's definitely worth learning about oxygen debt, oxygen deficiency. If you don't understand what the hell I just said, look up in a medical journal. Yep. Look up in a medical journal, do something. Just gotta text this really fast. So yeah, you can just look up in a medical journal. There's a lot of things on the oxygen debt you can always look up, and it explains it very well. So now I'll go over the 3 energy systems since I skipped that. I didn't even say on the guide. Since I didn't even say it on the guide, but 3 energy systems, your body has 3 energy systems. They're depending on how intense the exercise is. The very first energy system is called the phosphagen energy system. This is where you need energy extremely fast. Now, glycolysis is fast, but the phosphagen system is extremely fast. It supplies energy, it supplies ATP to your cells, an explosive force of energy for 7 to 10 seconds. Now, this number is numbers are always thrown around, they're always argued, like I say 7 to 10, so the book says 30 seconds, Dr. Muff says 15 seconds, this source says 18 seconds. All the numbers are different. It's really hard to find a set number. Again, first thing you realize is the body is not 100% explored. We find out new things about the body every single day. So this number can change. And the number can also change depending on an individual person. Obviously, a sprinter is more efficient at making ATP than a sedentary individual. So they might be able to last for 15 seconds as compared to someone for 10 seconds. And what I mean by 10 to 15 seconds is how long this phosphagen system happens. Now, the phosphagen system is when you need energy extremely fast. You're sprinting 100 meters, you're jumping, you're pole vaulting, you're in high jump, you need energy extremely fast. The phosphagen energy system is called the immediate energy system, another name. What it is it's abbreviated as PCR, phosphocreatine. Phosphocreatine is a molecule just chilling out in your bloodstream or chilling out in your cell cytosol. And if you need energy extremely fast, you can split this phosphocreatine, take the phosphate off of it, put it on an ADP that is also floating in the cell cytosol and form an ATP. This can happen extremely fast, and this is called the phosphagen system. So you form an ATP extremely fast. Now, another immediate energy system that's also in the phosphagen system is you can take an ADP plus another ADP, take one phosphate from an ADP, form an ATP. This is also an immediate energy source, extremely fast. And that happens through an enzyme called ATPase, ATP synthase. So these are all extremely fast energy systems. Now these only you have an limited amount of phosphocreatine in your system, in your cell cytosol. So this system can only supply energy maximally for a very short amount of time. Now this takes me to another supplement thing about supplementing with creatine. So supplementing with creatine is effective. It does work, but this is how it works. This is the mechanism of how supplementing with creatine works. Supplementing with creatine, this is what creatine does in the body. It does other things in the body also, but this is how what it does in the body involving muscular strength, muscular power. It forms that creatine, that phosphatidylate, so you form more PCR. So you would think if you have more PCR in your cell cytosol, you can ultimately form more ATP, and that is true up to an extent. So normally, without supplementing with creatine, you can use this immediate energy system for say 7 to 10 seconds. Say 10 seconds is your max. So now you supplement with a shit ton of creatine. So now you can stretch this system to say 20 seconds. So as you see, supplementing with creatine does work. It does give you more explosive strength. It does, like if you're say you're an Olympic lifter, you do snatches, and you do all these stuff. You need energy extremely fast. You're sprinting, you need energy extremely fast. Creatine does work. It does increase your maximum strength, your immediate explosive energy, to an extent. So this is why supplementing with creatine, if you're an endurance athlete, if you're nothing but an Olympic lifter, supplementing with creatine is pointless. You're wasting your money. You pee out most creatine anyways, but it does work. If you care about having bigger looking muscles but not being stronger, yes, take creatine. Because creatine it draws water into osmosis, so it does make your muscles look bigger. So if you care about having bigger muscles but not being stronger, then yeah, sure, take creatine. But if you want to be stronger, work out. Simplest way. Don't waste your money on creatine. But creatine does work. So that's the energy system. The second one is glycolysis, and the third one is aerobic respiration. So those are the three energy systems. Okay, so now we're on to muscles. Now again, mine are different than his, but my first question was describe the three types of human muscle fibers and their relationships, what they do, their characteristics, and all that good stuff. The three types of muscle fibers are type 1, type 2A, type 2X. Now, the reason I look is because every single class they call something different. Type 1 is always called type 1, but type 2A is always called type 2A, but type 2X is sometimes called type 2B or type 2X. So it's always different. He refers to it as type 2X. It's all different. I mean, it depends on what the class is, what he taught. But you have three muscle fiber types: type 2A, type 1, type 2A, type 2X, or type 1, type 2A, type 2B, whatever he depends. Type 1 is considered a slow muscle fiber, slow twitch muscle fiber. It's a big muscle fibers, like your back is type 1, or that's a bad example, but type 1 muscle fibers are big and slow. They're efficient, but they're big and slow. So they rely mostly on fats for energy. They have a lot of mitochondria. They have a lot of blood capillaries, high capillary density, a lot of oxidative enzymes, because they rely on aerobic respiration, that whole pyruvate to TCA cycle, forming a lot of ATP and breaking down fats. And they take a while to fatigue, obviously, if they're rich in mitochondria, and they form a lot of ATP. So you can memorize all the characteristics about these, or you can use common sense and think about them and know the concepts of it. So the concepts are, if type 2 is large and fatigue resistant and forms a lot of ATP, what do you need to form a lot of ATP? Well, ATP is formed in the mitochondria, so you need a lot of mitochondria in order to form a lot of ATP. That's one characteristic, a lot of mitochondria. Another characteristic, what else do you need to form a lot of ATP? Well, you need oxygen. That should be common sense. You need oxygen to form energy. Muscles live on oxygen. So what do you need to have oxygen? You need blood flow. Oxygen travels in the blood. So higher blood flow equals more oxygen. Oh, look, type 1 fibers have a lot of capillaries which deliver a lot of blood flow. Because blood travels in capillaries to get to muscles and tissues. So rich in mitochondria, have a lot of capillaries. Myoglobin is a way to travel oxygen. More myoglobin equals more oxygen, so it makes sense to have more oxygen. They know they take a while to fatigue. Why do they take a while to fatigue? Because they have a lot of oxygen. If they have a lot of oxygen, they have a lot of mitochondria, so they take a while to fatigue. So all these things, you can memorize the characteristics or you can know the concepts. Since they take a while to fatigue, what makes them take a while to fatigue? What makes them make a lot of ATP? What makes them do this? Know the concepts, saves you memorization. Type 2A is considered intermediate between type 1 and type 2X, or type 2B is an intermediate. So it has characteristics of both. While type 2A is fatigue resistant, has a lot of mitochondria, it's very large, it's called slow twitch muscle fiber. Type 2X, when we get to it, it's called fast twitch muscle fiber. It fatigues extremely fast, but it gives you energy extremely fast. Type 2A is intermediate, so it's an intermediate. There's really nothing to say about that. The characteristics, you would have to memorize these characteristics since it's intermediate, but it has a lot of mitochondria since type 2A does kind of act like type 1. It is fatigue resistant, but it has less capillary density, which means that it has less capillaries, so it yields less oxygen and less blood flow. And you just have to memorize those. And that's also called fast oxidative fiber. Oxidative means slow, fast. It means fast. Now, type 2X is considered a fast twitch muscle fiber. It's considered fast twitch because it is explosive. It yields energy extremely fast. It just uses the phosphagen system for energy, which is the immediate energy source, and uses glycolysis, which gives you energy faster than, say, aerobic respiration, or the breakdown into the citric acid cycle, all that good stuff. So now, since it yields energy extremely fast, and it depends on glycolysis and depends on the immediate energy source, let's guess the characteristics of it. If it depends on glycolysis, glycolysis does not happen in the mitochondria. So it wouldn't have any need for a lot of mitochondria. And yes, it does not have a lot of mitochondria. Since it doesn't depend on oxygen for energy, it shouldn't have a lot of capillaries. And yes, it does not have a lot of capillaries and does not have a lot of capillary density. Since it depends on mostly glycolysis, yes, it has a lot of glycolytic enzymes. And it tires extremely fast. I'm sorry, mistake. Fast twitch muscle fibers are large. Sorry. Type 1 muscle fibers are smaller. Or they're called slow twitch, fast are called. Type 2X are called fast twitch. And it's called fast glycolytic. So fast twitch tire extremely fast. The white, if you look at them through a microscope, the white because they lack blood. Blood is what makes things red. They have no need for blood. So because they use glycolysis does not depend on oxygen, so it doesn't need a lot of blood. Type 1 muscle fibers are red because, if you look at them on a microscope, because they have a lot of blood flow, they have a lot of capillary density, they depend on blood, they depend on using fats for energy. And they're called slow twitch muscle fibers. Now, question 2 is, how does muscle fibers change with training? Can you turn a type 1 muscle fiber, a slow twitch, into a fast twitch muscle fiber, and vice versa? The answer is no. You cannot turn a fast twitch muscle fiber into a slow twitch muscle fiber, and vice versa. But muscles are extremely adaptable. The body is extremely adaptable to any kind of stress. So with training, type 2 muscle fibers could mimic type 1 muscle fibers with enough training, and vice versa. Type 1 muscle fibers could mimic type 2 muscle fibers. So if you do a lot of sprinting, eventually your type 1 muscle fibers will act like type 2 muscle fibers and be more efficient at delivering energy extremely fast and fast twitch. Do they become type 2? No, they cannot change their morphology. But they are adaptable and they can act like the other muscle fiber. The type 1 muscle fiber could get more glycolytic enzymes. It can lose mitochondria. It can get more efficient at using glucose and using glycolysis. But ultimately, it will not change its morphology. What is the role in muscle contraction? Okay, so question 3, I combined every single question about muscle contraction. From explaining myofibrils, explaining all the filaments, actin and myosin, explaining muscle contraction, the neuromuscular junction, how calcium is evolved, what ATP does, everything about muscle contraction I combined in this one question. The question that I use is, what is calcium muscle contraction? Explain the Science filament theory and how muscles are fueled. So first thing you need to know, looking at a picture of muscles to understand it, but Everything about muscles is in layers. Really, everything in the body is in layers. You have an outer layer, an inner layer, blah, 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 it gets smaller and smaller and smaller. The outer layer of the muscle, if you went through the anatomy, is called the epimysin. Epi means around, mysin means muscle. And then you go beneath the epimysin, and you get to the perimysin. Perimysin is what surrounds a bunch of muscle fibers, if you went through the anatomy. And then you break it down even more, and you get to the endomysin. Endomysin surrounds an individual muscle fiber. And now looking at that muscle fiber, and these muscle fibers are the type 1, type 2A, type 2X. Now looking at these muscle fibers through a microscope, you see a lot of little lines called striations. Now if you look even deeper, these striations are actually repeating segments called sarcomeres or myofibrils. So myofibrils are the same thing as sarcomeres. Those are the smallest unit of muscle contraction. Those are repeating units. If you look at a muscle fiber, you have sarcomere, 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 sarcomere. Keeps going on and on and on. Now, if you look even deeper, these sarcomeres have different proteins called myofilaments. Now, these myofilaments are the actin and myosin that you hear so much about. And now we'll go through they're called different things depending on where they are. Now, you look at your muscle, it's like this, or your sarcomere. These two lines on my hands these are called the Z discs. These separate the individual sarcomeres. So sarcomere, Z disc, Z disc, sarcomere, Z disc, Z disc. Now looking even deeper, depending on where actin and myosin are located, depends on if it's called an A band, an I band, an M band, blah, blah, blah. Now the I band stands for isotropic. Iso means one, or the same. So the isotropics are, so here's a Z disc, going not to scale, but here's a Z disc. The I band are right here. They're inside the Z disc. These contain just actin. So if you look at them through a microscope, look at them through a picture, they're very light, they're very thin. Those are the I bands. They contain just actin. Going even more to the middle band, like right here, is called the A band. The A band stands for anisotropic. It's combined actin and myosin. So A band, it has actin and myosin in the middle. Now the very middle of the A band, you have the M line, like right here. The M line has just myosin. Very simple, M line, myosin. That's a very dark line. So if you're looking at it through a microscope, look at a picture, that's why myosin is called the thick chain, actin is called the thin chain. Actin is very thin. Looking at it through a microscope, that's what causes the striations. It's very thin and repeating segments. So Z discs are just different proteins. They're not actin or myosin. Don't worry about them. I band is just actin, so it's very light. And then you have your A band in the middle. The A band is actin and myosin. And then you have your M line, which is in the middle, intersecting the middle, which is just myosin. Or the M line is like this, in case he explained the H zone. The H zone is another line inside the M line, which is just proteins. I wouldn't focus on it unless he explained it. But the main things that we care about are actin and myosin in all the bands. The Z disc, the I band, the A band, the M line. Okay. So now when a muscle contracts, so say you have your sarcomere, and your sarcomere, and your sarcomere. When a muscle contracts, that sarcomere actually contracts. That's why it's called muscle contraction. Sarcomere gets smaller and contracts. So now it's very important to realize what happens to these individual discs or bands. Which ones get smaller, which ones stay the same, etc. Now, I'll go over the sliding filament theory and make more sense, but essentially you have your two bands. Now what happens when it contracts is it literally gets smaller. The myosin actually pulls the actin over bands. So what happens is the I bands actually disappear. So the actin, the I bands actually shorten. They do not disappear. They shorten because they're contracting. The H zone, which I talked about, I don't know if you need to know the H zone, but the H zone doesn't really. Shit, sorry, I had it backwards again. The H zone is the band with just myosin. The M line is a band with proteins. Sorry, had it mixed up. So the M line is just proteins. The H zone is the band with myosin. So when it's contracting, the I band gets smaller. The M line the M zone, or whatever you want to call it, that has just myosin, disappears because it's being overlapped, it's contracting. The A band stays the same size. That is what is important. After this whole question of all the bands changing size and everything, the most important thing to know is the A band stays the same size. That was a question, well, I shouldn't say it was, but that will probably be a question when you take the test. What happens during muscle contraction? What bands change sizes? The A band stays the same size. Okay, so now talking about what actually happens when muscles contract. Well, muscles contract. But looking at two, you got to imagine two individual sarcomeres. So remember, muscle fibers, a muscle has thousands and thousands and thousands of fibers. We're just looking at one muscle fiber, which has thousands and thousands of sarcomeres. Everything in the body is redundant. It repeats many, many, many times. So we're looking at one fiber. We have millions of sarcomeres on it, but muscle fascicles, which are a combination of fibers, actually contain many, many, many fibers. So really, there's another fiber like a nanometer. That was my boss on Flash Notes. But muscle fibers actually contain, muscle fascicles contain many, many fibers. So what really happens is they contract. So this fiber pulls this fiber to contraction. Sliding filament theory, the filaments slide past each other. Now that might not make sense. Look at a picture. Look at a diagram. Go to YouTube. Type in sliding filament theory. Watch a video. That's the best way to learn. But essentially what happens is myosin pulls actin over. In order for myosin to bind to actin, or myosin has to bind to the actin. Now, if you zoom into actin, actin is covered by a protein called we'll go back to the beginning first. Actin has many, many, many little spots for myosin to bind. It has many myosin binding spots. But actin itself is covered by another protein called tropomyosin. So vision, this actin's a globular protein. It's wrapped around each other. So vision this globe of proteins wrapped around each other. Each individual globe has little holes for myosin to bind and pull at the actin. But another protein, think of a wall. A wall stands between myosin and these holes in order to bind. And this is called tropomyosin. So we have to move this tropomyosin in order for myosin to bind. How will we move tropomyosin? Well, on this tropomyosin, on every, I don't know if you know what orientation it is, but on every 7th actin globe, there's another protein called troponin. It's a regulatory protein. So troponin, when calcium, which we'll find out, calcium is what causes muscle contraction. When calcium binds to troponin, the troponin signals the tropomyosin to get the hell out of the way. So myosin can bind to it, and now myosin can pull the actin to contraction. And then when calcium leaves the muscle, troponin goes back over, tells tropomyosin to cover it, contraction stops. So that's what happens. How does neurostimulation lead to muscle contraction? I believe his question was explain the neuromuscular junction and all that stuff. Okay, so everything in the body happens. You'll find out on the third test, I believe, where Eddie takes over, who's a much better teacher than Dr. Moffat, I believe. I'm going to say that. But Eddie takes over, and Eddie talks about all neuromuscular junction, the motor unit, all that stuff. Or in my class, at least. I don't know how your class is going. So everything happens through action potentials. The body communicates through electrical potentials. So in order to do this, an action potential travels from a neuron to something called the neuromuscular junction, which is the synapse between the muscle and the end of the neuron. That little tiny space called the neuromuscular junction, or the synapse. So what happens at this little synapse is the action potential, the action potential releases acetyl-coA from this neuron to the tip of the muscle. So acetyl-CoA travels to the tip of the muscle, or travels past the neuromuscular junction to the motor end plate. There's many names for it, but it travels to the muscle. Acetyl-CoA causes a bunch of sodium molecules to enter the muscle. When this happens, it causes another action potential inside the muscle. So this action potential travels into the heart of the muscle because, again, from knowing that everything is in layers, you have to get into the middle of the muscle. That's where the sarcomeres are. So this action potential has to get into the middle of the muscle. So in order to do this, it travels down something called the sarcolemma. The sarcolemma is just a tube that leads into the middle of the muscle. So the action potential travels down the sarcolemma to get to something called the T tubules. Yeah, the T tubules. So it gets to the T tubules. Sarcolemma, sarcoplasmic reticulum, same thing. But it travels down the sarcoplasmic reticulum to get to the two T tubules. At the T tubules, you have something called the terminal cysterias, which store the calcium. So when the action potential reaches the terminal cysteria, which is inside the muscle on the sarcoplasmic reticulum, this signals the terminal cysterias to release a shit ton of calcium. So now all this calcium goes into the muscle, and now the calcium is the calcium concentration increases inside the muscle, and you have a lot of calcium inside the muscles. So thinking, what does calcium do into the muscles? It tells troponin to tell tropomyosin to get the hell out of the way, so myosin can bind to actin and cause it to contract. So this whole process was just to get calcium released into the muscle. So yes, and then your job is accomplished, the muscles contract. Remember the I bands, when the muscles contract, they shorten. The A band stays the same size. The H zone in the middle, which is just myosin, disappears. And this is muscle contraction. And this happens many, 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 many times. This is how muscles contract. So muscle contraction always happens until, well, if you need a calcium to remove tropomyosin from the actin, it makes sense that once we lose calcium, once calcium decreases, muscle contraction will stop because tropomyosin, okay, I have to answer this. Hello? Hey Mike, what's up? Can I call you in 30 minutes? I'm making a video right now. Okay, it's okay. Bye. Yeah, so again, Boston Flash notes, this call is allowed. So without calcium, muscle contraction will stop. Question 7 is, what is the difference between a muscle fiber, a myofibril, and myofilament? Answered already, but a myofilament is actin and myosin. A myofibril is the same thing as a sarcomere, that's each individual repeating unit. A muscle fiber is, well, slow twitch, fast twitch, etc. That's what holds them up. That's what the biggest unit of the muscle fiber, fast twitch, slow twitch. Can't really explain more than that. What is the sarcoplasmic reticulum? Sarcoplasmic reticulum is, let me see. At this point, you all had anatomy. So the sarcoplasmic reticulum is like the endoplasmic reticulum of a cell. It's what forms all the proteins and packages them. But the sarcoplasmic reticulum is the main pathway in muscles that the action potential travels on to get into the middle of the muscles. So you have a muscle, neuron, action potential travels, jumps to the neuromuscular junction, causes sodium to enter the muscle. Sodium causes another action potential. The action potential travels into the middle of the muscle via the sarcoplasmic reticulum. Once it gets into the middle of the muscle, you have your sarcoplasmic reticulum. Then it enters the T tubules, which are small tubes. They have terminal cysterias, which are sacs on the muscle in the sarcoplasmic reticulum. Inside the muscle, they release calcium. So it all starts with the sarcoplasmic reticulum. So sarcoplasmic reticulum brings the action potential into the muscle. But the actual calcium is released from the terminal cysteria. Again, go with what he says. Physiologically speaking, correctly speaking, it is released from the terminal cysteria. If he says it's released from the sarcoplasmic reticulum, go with that. 10 is, how is ATP involved in muscle contraction? So this is like the end point of why we went through glycolysis. We formed all this ATP. Remember that glycolysis formed 38 ATP. Fatty acids formed a lot more ATP. Why did we form this ATP? So far, we just formed ATP. We didn't use it for energy. This is how the ATP is actually used for energy. It allows muscle contraction to happen. So it causes, so once calcium bonds to troponin, moves toward myosin, all that good stuff, myosin has to attach to actin now. It's the next job. But myosin cannot attach to actin because it needs to be powered. It has to be activated. That's what it's called. It has to have some energy into it. By itself, it's just useless. So in order to cause myosin to attach to actin, ATP gets hydrolyzed to ADP and gets split, and this causes the myosin head to be activated, and now it has a bunch of energy. It's jolted. It's just like caffeine causes a human to be energetic. ATP causes myosin to be activated. So it stimulates it. Now the myosin can attach to the ATP, pull it, causes a contraction. It's called a power stroke when that happens. So now it causes contraction. But the next step is, so now actin is binding to the myosin. These form a cross bridge called the actin-myosin cross bridge. This is a pretty damn strong bridge, can't really break. So in order to break this bridge, another ATP molecule has to split the actin and the myosin. And so myosin binding to actin really takes two ATP, one to activate it, one to split it. And this keeps going, activate, split, activate, split. This is the point of ATP. Now some real life examples to visualize this. Everyone's had a Charlie horse or muscle spasm. They know what they feel like. They hurt like hell. If you feel your muscle is literally quivering and contracting, and it's contracted and everything. It hurts like hell. This is literally what's happening in your body. Myosin was activated, binds to an actin via one ATP. You form that really tight cross bridge, the actin-myosin cross bridge, but another ATP was not there to break that cross bridge. So since you can't break that cross bridge, the muscle stays contracted. When the muscle stays contracted, you get a Charlie horse. That's what's happening. That's what causes the muscle spasm. It's very painful. This is another real life example is rigor mortis. That's how you pronounce it. When someone first dies, their muscles are, you can't bend their muscles. The muscles are stiff. So, like if you see videos or something, when someone dies during a muscle contraction, so say they die when they're like doing this or something, well they die immediately. Well, you won't be able to lower the muscle because the muscle. Well, you can lower the muscle because this is a joint, but you won't be able to move the muscle because the muscle stays contracted. Because when you're dead, obviously you do not make ATP, so you can't decontract that muscle. Now, eventually, over time, with formaldehyde and all that good stuff, you can cause that actin-myosin bridge to break. But without ATP, you can't break that bond. Real life example, Charlie horse. Easier to learn with real life examples. Question 11 is how do muscle types differ? This was explained. Type 1, slow twitch muscle fibers, a lot of mitochondria, a lot of capillary density, red, slow oxidative, depend on fats, a lot of oxidative enzymes, all that stuff. Type 2A, it's in between. It's called fast glycolytic, or fast oxidative, because it has oxidative properties. It has a lot of mitochondria, less capillary density. Type 2X, called fast twitch muscle fiber. It's very, very fast and very, very explosive. But because of this, it's explosive. It tires out extremely fast. It's white because it doesn't have a lot of mitochondria, it doesn't have a lot of blood flow, it doesn't have a lot of capillaries, has mostly glycolytic enzymes because it depends on glycolysis, everything. 12, what is the relationship between fiber type distribution and performance? Easy question. If you have a lot of slow twitch muscle fibers, whatever activity you're doing probably depends on a lot of endurance and a lot of, getting energy slow. Depends on muscles not fatiguing fast, all that stuff. So you're probably an endurance runner or a marathoner. And what do you know? A long distance runner or a marathoner has mostly slow twitch muscle fibers. Now, if you're a sprinter, you need energy extremely fast. Or if you're a long jumper or a high jumper or something, you need energy extremely fast. So it wouldn't make sense to have a lot of slow twitch muscle fibers which give you energy over a long period of time. So you probably need a lot of fast twitch muscle fibers to give you energy extremely fast. And thus sprinters have mostly fast twitch muscle fibers. Now, if you're sedentary, if you're a weightlifter, your body really doesn't have a predominance of fast twitch or slow twitch. It's like 50-50. Now, a real life example is like me, for example. In the graduate physics class, you do an exercise on a machine called Biodex, which can estimate your percentage of slow twitch or fast twitch. Now, the only way to truly estimate your muscle fiber type is to take a muscle biopsy and actually look at the muscle. But a Biodex can give you an estimate, and I'm around 75% slow twitch muscle fibers, which makes sense because I am a cross-country runner, triathlete, I ran marathon, so yeah, I'm mostly slow twitch muscle fibers, so that makes sense. Now, if you take like a sprinter from FSU, they're mostly fast twitch muscle fibers. Okay, now the question is, how does training affect oxygen deficiency, oxygen debt? This is a tricky question because from my understanding, and from also understanding in graduate books and peer-reviewed articles, training does not no amount of training can take away oxygen debt and oxygen deficiency. You always have an oxygen deficiency. Remember, starting oxygen will always differ from the oxygen you need to start to do the exercise to reach steady state. So you always have oxygen deficiency and oxygen debt. What I think he's asking is, with training, it is true from a personal standpoint, everyone's done it. With training, you do get better at exercising, so your oxygen debt does decrease. You do reach steady state faster. So in that extent, training does make you reach steady state faster. But you always have an oxygen debt and oxygen deficiency. So with that, it's kind of ambiguity. I really don't know what to go with because he's not specific what he's asking for. But you do reach steady state faster the more in shape you are. Everyone knows that. Take someone who's never ran a mile in their life, tell them to go run 5 miles. They will never reach steady state. They will be out of breath like on mile 1 or even faster. Take a cross-country run and tell them to go run 5 miles. It would be extremely easy for them. They reach steady state extremely fast. Their body is more efficient at that exercise. Question 2 is bioelectric adaptations to exercise training. This is very simple. Everything about the body, the muscles, everything is extremely adaptable. The body can achieve many incredible feats of physical strength, many incredible things by exercise. The muscles are very myoplastic, which means they can adapt to anything. This is why strength training does make your muscles stronger, makes your muscles adapt. What it actually does is it does break down your muscles. Look at your muscle fiber or biopsy after you work out. It looks like shit. It's completely fucked up. All the Z discs are messed up. All the actin-myosins are broken. You literally destroyed your muscles. But with training, with rest, now your body adapts to it, and it knows next time it reaches that same stress level, it has to be stronger. So it actually does get stronger. You don't build more muscle fibers. You build more myofilaments, more fast twitch and slow twitch, more sarcomeres, more myofibrils, more enzymes, more oxidative enzymes, more glycolytic enzymes. So your body gets better at adapting, and it's very adaptable. So biochemical, you get better at storing glycogen with exercise. You build more enzymes, you build more proteins, you get more adaptable in exercise. This is the point of bodybuilding. They get stronger. Your body adapts. Your body is very adaptable. Okay, that goes over everything with my guide. If there's any more questions, post them on the Facebook page. I'll answer them. I will be posting this video for free since the video conferencing did not work. So know that I'm posting this for free. So I just donated 90 minutes of my time talking about tutoring when I could have been tutoring someone else. So yeah. So I'm here to help you guys. That's what I'm saying. So any questions you have, don't hesitate to ask them. There is no stupid questions when it comes to this stuff. Ask these questions, because I guarantee whatever question you have, someone else in this class out of 100 people probably had the same exact question. So ask questions.